Alright, we're doing this flipped classroom stuff. Alright, today we got polynomial functions of degree greater than 2, section 3.1. Alright, not too bad stuff here. Let's knock it out. Start with a definition. A polynomial. For future reference, I'm going to abbreviate polynomial by the word poly. Alright? A polynomial function of degree n has this form. F of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 dot. It just continues down. A sub 2 x squared plus a sub 1 x plus a naught, where a naught cannot equal 0. Alright, so this is the general form of a polynomial. And we'll define all the parts here, but it just goes down as you can see there. Alright, so let's define the terms. Let's see. We'll call these notes. The degree of a polynomial is just the highest exponent. Alright. Your a sub n, a n minus 1, all the way down to a naught, they exist in the real numbers. Alright. N must be positive, must be a positive whole number. A sub n is the leading coefficient. And a sub naught is just a constant term. It has no variable on it. Alright, so this is the way we're going to define the polynomial function. Alright, so let's just give a quick example of what these terms mean. So if I said f of x equals 3x cubed minus 5x to the 4th plus 2x minus x squared plus 1. We can rearrange that going from highest exponent as negative 5x to the 4th plus 3x cubed minus x squared plus 2x plus 1. So our exponents are now in descending order. So the degree of this is what? No, I'm kidding. I'm not going to do that. It's 4. All right, 4. A sub 4, which is your a sub n here. N. So your leading coefficient is negative 5, and your constant term, which is a naught, is 1. All right, so that's how we apply these definitions to that function. I'm going to be going in and out of the camera. You'll get over it. This is the first trial run. We'll get better as we go. Don't worry too much about it. All right, let me give you a couple special cases. These are in your book. Forget the page number, but I'll give them to you right here. So if we have a polynomial of degree 0, 1, or 2, these are some special cases that we'll look at here. All right, so the form of f of x in these cases, well, this is just f of x equals a constant term, right? Because the degree is 0 on your variable. And the graph of f in that situation is just a horizontal line. Alright. Of degree 1, our form is going to be f of x equals a sub 1x plus a naught. Right? And this is just a line with slope equal to a sub 1, right? So this is just y equals ax plus b. This is something we're all very familiar with. Degree 2, f of x equals a sub 2x squared plus a sub 1x plus a naught. And again, you should be familiar with this. This is a parabola with a vertical axis. Alright, and again, standard form of a form of parabola, ax squared plus bx plus c. Same setup here. Alright, this is I want you to take note of this here. All polynomial functions, so all polynomial functions are continuous functions. We've talked about continuous functions before. But that basically means they can be drawn without lifting our pencil. So something like this, it's smooth. Yes, it has curves, but there's no points, and I can draw the whole thing without lifting my marker. Whereas in this situation, if I did something like this, and then jumped, I had to lift the marker. It's not a continuous function, and therefore we can't really work with those. Alright? If I'm going too fast, the advantage of this is you can pause the video, or rewind it, or turn it off. Fail your next test. I don't really care. Alright, let's do turning points. I like that I never, when I'm doing it this way, I don't actually have to turn back and look at anybody. Right? I can just look at the board. I don't know. I'll get better at it. You'll get used to it. It'll all be good. Turning points. Alright, so recognize as you move forward in pre-cal, right? Move forward in pre-cal, get into calculus. Some of you will go on, some of you won't. Right? Turning points. You're going to see more and more advanced graphs of various functions, right? My wife's sitting behind the camera, so that's something. All right, let's see. Some more advanced graphs. Have what we call turning points. It's not a mystery. This is exactly as it sounds, right? So here's your definition. Turning points. Let's see. They're just points on the graph. On the graph of f, where it changes from increasing to decreasing, or vice versa. Okay? So in this crude graph here, this is a turning point, and this is a turning point, right? We're increasing, now we're decreasing, and then we're back increasing. So a turning point is exactly what it sounds like. It's just where it changes from increasing to decreasing. All right? So a more elaborate example would be something like this. If I had a function that hit here, and here, here, and here, well, these points are called turning points. So R, S, T, these are your turning points. Okay? We'll come back to that, deal with that a little more in detail. Here's a note I want you to get. This is really important. It'll help you later on in this class, and especially in calculus. An nth degree polynomial has at most n minus 1 turning points. Recognize what this is saying. An nth degree polynomial has at most n minus 1 turning points. That means if we were to deal with something with a degree of 4, it has at most n minus 1 turning points. That means that the most turning points it can have is 3. All right, and we'll look at an example of that later. All right, so that's something I want you to really get. Okay, let me erase this top part here. All right, another name for turning points. I won't use this a whole lot, but you'll see it in your book. Turning points are also called relative extrema. Relative extrema. So, for example, if I gave you a graph that looks like this, right? Well, there's multiple mins and maxes here. This is a max in this location, and this is a min in this location. But this is the ultimate max, or the relative max. And that's your relative min. Okay, so relative extrema, or relative max, and a relative min. Alright? Alright, the next thing is probably the most important thing we've done all year. It's the intermediate value theorem. This one is specifically for polynomial functions. But the IVT is what I'll call it, the intermediate value theorem, is going to be the basis for pre-cal all the way up through the rest of your mathematical careers. All right. So here it is, the intermediate value theorem. This is the part of the video that I really want you to pay attention to. All right. If f is a polynomial function, right, and f of a does not equal f of b. So in other words, we don't have a straight line. F of a is not equal to f of b when a is less than b, comma, then f takes on every value between f of a and f of b on the interval, recognize it's a closed interval, ab. Intermediate value theorem. It's one of the most important theorems in calculus. You'll use it for many years to come, so get used to it. We'll look at a couple of ways to use it here in just a second. Any questions? Nothing? I really like this method of doing things. It's like I don't have to listen to Sam complain or Andrew distract other people or anything like that. It's nice. Alright, there's a couple of ways to do this. Let me put the graph on the board first and kind of explain what this definition is really saying in picture form. Right, so let's say we have a point A here and a point B. These are two x values. So, and let's say f of a is up here somewhere, right? And let's put f of b down here. Okay, well, let's say our function works out such that this is the point A, f of a, and let's put the point down here, b, f of b. And it doesn't really matter what our graph looks like. Let's just say it's a downward slope there. Recognize that every value, so let's go back to what the intermediate value theorem is saying. Right? The intermediate value theorem says f's a polynomial function, f of a not equal to f of b. Well, we've established that fact. And a is less than b. Well, certainly a is less than b. Then f takes on every value between f of a and f of b on the interval ab. So that, in other words, for every x value between a and b, all these x values, f takes on every y value. So that's a picture form of what the intermediate value theorem is really saying. All right. So let me look at it in a slightly different way, in kind of common language here. So here's basically what the IVT is telling us. The intermediate value theorem says. It tells us if W is some number between f of a and f of b. So in other words, f of a less than w less than f of b, right? Then there exists at least one number called c between a and b. So a less than c less than b. These are less thans. Jonathan Brand always complains about my less thans. Such that f of c equals w. So let's put that in picture form, and maybe this will complete the idea. So we've got A, we've got B. So this is telling us C is between A and B. Doesn't matter where, pick a spot. C. Right? Then we've got f of A, and we've got f of B, and then we've got some number W that's between those two things. Right? What the intermediate value theorem is saying is, here's A, f of A, here's B, f of B. If this is a continuous function, then there is, well, that's not going to work actually, sorry. It's got to go up this way. Then there is some number up here that works for W and C. So whereas this is f of A for the x value A, and this is f of B for the x value B, this is really f of C for the x value C. We're just calling it W. Alright, so there's two picture forms. They're showing you basically the same thing, just in a slightly different way. Hopefully you got one of them. Alright, so let's do an example that may clear it up for you. How's the video looking?
Good.
Yeah. Yes, yes, yes. Don't you guys really like that I'm teaching in a hoodie and sweatpants? Yeah. Alright. Here's an example. Let's let f of x equal 2x to the fourth plus 3x minus 2. Right? I'll tell you what. I got another example in here I'd rather do. Doesn't matter. Yeah, let's do the other example first. I'll come back to this one. Let's let f of x equal this one. X to the fifth plus 2x to the fourth minus 6x cubed plus 2x minus 3. Right? We want to show that f of x has a 0 between the values 1 and 2. Now remember what a 0 is. We've defined a 0 to be when it crosses the x-axis, right? Or when y equals 0. So anytime a function crosses the x-axis, we call that a 0. So we want to prove that this function has a 0 between the numbers 1 and 2. So graphically, we don't know what this graph looks like, but we know we're looking between the values 1 and 2. What we want to show is that somewhere between here, there is a solution that causes this thing to cross the x-axis. All right. So here's our solution. F of 1, well, f of 1 is just 1 plus 2 minus 6 plus 2 minus 3, and I think that equals 4. Negative 4, sorry, if my math's correct. F of 2, well, that's 32 plus 32 minus 48 plus 4 minus 3. This comes out to a positive 17. Well, you say, how does that show us anything? Well, let me write this next thing out and you'll see why. Finding this value and this value show us that there's a 0 between the values of 1 and 2. So here it is. This is a big note. Put a star beside it, put 2 stars beside it. A consequence of the intermediate value theorem is that if f of A and f of B have opposite signs, then there is at least one number, C. That's a C. That's a C.
I can't see it.
Right now?
Yeah, you're blocking it.
Oh, yeah, I know I'm going to block it. They'll get over it. They'll see it in a second. C, between A and B, such that f of C equals 0. Alright, so graphically, this is saying this right here. So let's say I've got an A and a B. So here's my A value, here's my B value. And somewhere down here is the point A, f of A, and somewhere up here is the point B, f of B. The intermediate value theorem says because these things are negative, f of A is negative, f of B is positive, that this graph has to do that in some way, shape, or form. It has to cross the x-axis at least one time, and there's your value C. So going back to our example, we've got f of A, or f of 1, is a negative number. F of 2 is a positive number. Therefore, we don't have to do anything else. We don't have to graph it. We don't have to put it in the calculator. We don't have to do anything else to show that there is at least one 0 between these two numbers. It crosses the x-axis at least one time. You can punch it into your fancy calculators and see what that graph looks like if you want to. All right, that's where I'm going to cut it off for right now. This was the first trial run. I like it. I mean, it's roughly, what time is it?
We've been talking 23 minutes.
It took 23 minutes, and it's almost 7 o'clock on Sunday night. You're welcome. All right. But it's a 23-minute video. It's 20 minutes shorter than class. Think of it that way. So we'll see how it goes over. My plan. Hey, that was my phone. My plan is to actually put all these definitions into a PowerPoint, and then just have the videos for examples. But we'll see how this goes. All right. I've got to figure out a cool sign-off. I haven't figured that out yet. I'll see you.
Bloopers.